thank you very much for inviting me, and thank you for coming. Thanks to the organizers for organizing this nice meeting. So I'm going to be talking about some features of one measure of entanglement, which is called the logarithmic negativity, and specifically for 1 + 1 dimensional quantum field theories, not necessarily integrable, although integrability has been an inspiration for this project. I last gave this seminar in Paris, actually, so Denis has already seen it. And when I gave it there, he said I should call these negative features of universality. I don't think that's fair. First of all, just a little bit of background. So this is essentially what I will talk about today is about to be published in the APSA, and this was work I did with Benjamin, that cannot be here just now because he's teaching. He will be here later. And his postdoc, Olivier Blondeau-Fournier. So this is already accepted for publication, and now we are working on an extension of that work specifically for the free boson theory, which is quite simple and where we can do lots of things analytically. Hopefully this will be published soon. This is with the same authors and also with my student, Davide Bianchini. However, the techniques that we use are very much related to work we did quite a long time ago, which was some work I did with Benjamin and with John Carty, already going back to 2008. And it was really in this paper where we set up all the machinery that we have been using since to try and tackle regions of entanglement when you have actually finite correlation, so massive degrees of freedom. So if you've never heard of this sort of thing, you can find the basic ideas better explained in this paper. Okay, so you've all seen this sort of state, Bell state. And the sort of question we ask in this field is, okay, for a state like this, of course, we all know since university that this is a highly entangled state of two particles. In fact, it has maximal entanglement for this kind of setup. And it's actually very easy to understand just by looking at the state why this is the case and even to quantify the entanglement. But the question that people have been asking for many years already is what happens when we instead have much more complicated systems. So in general, many-body quantum systems. So how can we say something about the entanglement that is stored in the state of a many-body quantum system? Can we say anything at all? And even if this system is integrable, which is what many of us know best, still the states of integrable systems are very complicated. So anything that gives us non-trivial information about them is an interesting thing. So that's a motivation to look for measures of entanglement, and when you do that, the first thing you have to ask is actually what is a good measure of entanglement? So how do you find a function, mathematical function, that provides a good measure? And people ask this question, have been asking this question for a very long time, and I think it started mainly in the area of quantum information, where people were particularly concerned about this. And of course, there's a lot of work around that, but there is in particular a review I found, which I quite like, by Plenio and Birmani from 2005, where they actually, they reviewed actually all the measures of entanglement they know about, and they review their main properties. What are their main features as mathematical functions? And they explain that in quite some length, but there are some features which are quite easy to understand, quite obvious that you want to have them. One of them which, is this. So it should be what they call an entanglement monotone. So somehow it should be a function that measures entanglement. So if there is more entanglement, it should grow. If there is less entanglement, it should be smaller. That's kind of intuitive in some parameter. And in the language of quantum information, what they usually say is that it should not increase under lock, which stands for local operations and classical communications. So under certain transformations of the states, there should be no increase of entanglement, therefore no increase of whatever function measures entanglement. It should be invariant under unitary transformations. That's also natural to expect. It should vanish for separable states, so states that are not entangled at all, which are completely separable, we intuitively think they don't have entanglement, and so a measure of entanglement should give 0, essentially, for those states. And equally, it should not vanish for non-separable states. So there shouldn't be states which are not fully separable where the entanglement or any measure of entanglement is going to vanish. These are quite sensible things to expect. And if you look at this review, you will see that actually in quantum information, often people have asked for much more stringent requirements than this. So something that people often talk about, for example, is the notion of convexity of these functions or continuity or things like this. But I don't want to go into those details. That's not really my area, but just to give you an idea of what the background for all of this is. So in particular, thinking about all these ideas, people a long time ago came up with in particular two measures of entanglement that have now become very popular, especially among people with my sort of expertise in low-dimensional quantum field theory. One of them is the bipartite entanglement entropy, or von-Neumann entropy, and also there is that measure I'm going to talk about today, which is the logarithmic negativity. Both of them have a long history, and logarithmic negativity, I have to confess, I haven't yet got to the bottom of it, in the sense that every time I go to a conference, someone will say, and this paper should also be cited, they also did it first. So I'm supposed to write a review next year about this. I'm sure I'll get to the bottom at some point. But what is obvious is that people have talked about this logarithmic negativity for a long time. And as far as I know, these three authors here, three papers, Isert, which is actually his PhD thesis, then Vidal and Verna, and then Plenio, are the ones most often cited because they all contributed to proving that this is a monotone, an entanglement monotone. So they prove monotonicity of this function. Then before that, actually other people, even quite separate from the study of negativity, they prove other features of this function. One of them is Peres, that's often cited, because he actually particularly worried about some features of the reduced density matrix that is involved in this formula for the negativity, and we'll come back to that later. But what people now understand is that these are good measures of entanglement in the way I tried to describe before, so they have been very extensively studied. And in particular, in the last years, in the context of conformal field theory, there's been a lot of work led by John Carney, Pasquale Calabrese, and many of their collaborators. So although I'm going to talk about negativity, I think it's useful to introduce first the entanglement entropy, because some of the ideas used to define negativity actually are related to ideas that are involved here as well. And entanglement entropy somehow is slightly simpler to define. So the idea is always to consider bipartition. So actually all the measures of entanglement, as far as I know, that people use, they always have to do with bipartiting, a bipartition of the system. So you start with a quantum system, you divide it into two parts, or you consider two subsystems. They might be complementary or non-complementary, but you always ask the question, what is the entanglement between this part of the system and this part of the system? So hence the bipartite idea. In the case of the entanglement entropy, it turns out that the parts of the system you consider are usually, at least in this setup, are complementary. So if you think of a many-body quantum system, like a spin chain, which is simple to understand for us, you would have a configuration like this, where you consider, for example, a set of L spins in the middle of the chain, and then the rest of the chain. And just to make things easier, you can have periodic boundary conditions. So you have A and the rest, A bar, if you want. And associated to the state of this many-body quantum system, you can define a reduced density matrix. So if phi is the state of the system, which could be the ground state or an excited state, it can be any state in principle. People have mostly studied the ground state, but actually also excited states are interesting. Herman has done some interesting work on that. In any case, you define this object, so it's a reduced density matrix in the sense that the degrees of freedom of the complement of A are traced out. And so we get a density matrix which is non-trivial now, simply because we forgot about one part of the system. And this is all here, I'm thinking about zero temperature, so there is no entanglement due to the presence of a temperature. It's purely quantum. That's what we want to measure. In terms of this reduced density matrix, you can define this, which is the quantum analog of Shannon's entropy. So that's the definition, simply that. Now, it turns out that computing this directly in many-body quantum systems is generally difficult, not if you have numerical recipes. So if you have DMRG, of course, you can often compute the eigenvalues of this reduced density matrix, and if you know the eigenvalues, you can compute anything. You can compute von Neumann directly. But if you want to do analytic computations, it's often actually easier somehow to approach this quantity by starting with other quantities, other types of entropies. And there are various types, various definitions people have come up with. One of the most commonly used is this Renyi entropy. But also Sally's entropy has a similar definition. And really what characterizes both of these quantities is that there is an additional parameter in the definitions. There is a number n, which, as you will see later, in many contexts is natural to consider it to be an integer, a positive integer. But in fact, this can be defined for n integer or not. And what you have here in red is this object, this trace of reduced density matrix to the power of n. Now it turns out that physically speaking, actually it's easier to find an interpretation for this object than, for example, for this object here, rho log rho. And that's one of the reasons why somehow there's been a lot of work looking at Renyi entropy, trying to compute this trace of rho to the power of n, and then from here, trying, if you can, to get there by taking the limit n to 1, because actually when n goes to 1, both of these entropies reduce to the von Neumann entropy. Yeah?
Raja, usually all these arguments present picture like yours, in which we have a system with, from the space point of view, are separated into two sets.
Yeah.
Imagine that you have a Lib linear where the particle can move around. You have n of them.
Yeah.
Imagine I integrate on part of it, n third, n half. You choose it, the fraction.
Mm.
How do I compute this, and how shall I expect to scale?
I don't know. Particles are.
I want to say most of the time people focus just on space portion.
Right.
I mean, the notion can be much more general. I mean, you are partition your system in different ways, not necessarily space-wise.
Yes, that's true, but I mean, I don't know about that. The honest answer. I don't know, maybe somebody here has.
Yeah, so people look into that, including myself, for example, for quantum Hall states, where you have the two options. You can do spatial bipartitioning or subset of particles. And it turns out, you get very different information from the particle entanglement picture, so to say. For example, exclusion statistics or excitation, things like that. So it's a very different probe of the system.
But you have also scaling law in that case? Like here you have the typical area, scaling law and stuff.
No, not so clear. You get suppression from a maximal value due to correlations, and you're probing such many-body correlations.
Okay, so in particular, there's this another way of expressing all this is that you can get the von Neumann entanglement by doing a derivative of this trace of rho to the n, and then taking a limit when n goes to 1. And the fact that you can do this is often referred to as a replica trick. It leads to a notion of replica theories and multi-sheet Riemann surfaces. I'll talk about this later. And this has to do with a particular interpretation of this trace of rho to the n, which really only makes sense when n is integer. So in other words, you can think of this quantity here as a partition function for a system which now consists of n copies of your original system, which lives on a particular geometry. And once you take that step, then there are certain methods that you can access which are quite useful to do computations of these kind of things. So I'll come back to this a little later. Motivation for studying entanglement, I think probably all of you know some motivation, but of course it gives us information about the state of a quantum system that in itself is interesting, and it's a sort of information that's a bit different from what we are used to. So it doesn't come from computing correlators, which is what most of us will think of when we think about information about physical system. It has to do with something quite different. What has made this very popular in our community, I think, is that at critical points and even near critical points, the entanglement entropy displays what people refer to as universal behavior. And probably the best known formula, which Giuseppe was already referring to in this context, and the one that probably illustrates that universality best, is this formula here, which essentially tells you that in a 1 + 1 dimensional CFT, or at a critical point, the entanglement of a block of L spins scales as the logarithm of the block. So essentially it grows. If we take a bigger and bigger subsystem, the entanglement gets bigger and bigger, which you will expect when you have infinite length correlations. But what's the universal part of this is that the coefficient in front of this log really is a number that is universal and that characterizes the critical point you're looking at. And that number generally is proportional to the central charge. And if you generalize it a little bit, you can even write the effective central charge if your theory is not unitary, which is something we studied recently. But generally, you would know this formula with a C in here. So just by doing a computation of entanglement entropy, if you are studying a system numerically, for example, and you're not quite sure if it has a critical point or what critical point it is, you could classify the universality class of this critical point just by doing a computation of entanglement. And that idea is very powerful in terms of numerics, to the extent that it is now, I think, widely believed that this is the most efficient numeric approach to actually classify critical points. And many of you here actually have used it and have experience with that. So I just wanted to show you an example which is very nice. I think for many of you here this is not necessary, but maybe for some people that are a bit less familiar with this is a nice example to show, because it shows you all this behavior I was talking about. So there's one particularly easy model to study, the compute entanglement for, which is the easy model. This can be mapped to few fermions, and therefore actually the scaling limit can be taken exactly. And well, we can see this scaling law I just talked about. And this model has a feature which is interesting, which is that it actually has two different scaling limits in a way, depending on whether h is 1 or bigger than 1. If h is 1, as you probably know, this has a scaling limit which is described by a free fermion, massless. So it's a CFT with c equals a half. But if you take h bigger than 1, the scaling limit gives you instead a massive quantum field theory, which is the Ising field theory, which has one particle. And so we should see a difference in the behavior of entanglement due to this change. And indeed you do. If you do a calculation, and this is some numerics we did, but of course this was done by other people much before us. If you do a computation of the entanglement of a block of L spins, you see indeed that for h equals 1, you have logarithmic growth very clearly. That's the upper curve. And you can even do a very precise fitting of that growth. And if you do a fitting, you see you identify the central charge a half very, very precisely, because for Ising you can do that very exactly. You will have some non-universal constant as well, which you can give an interpretation to, but it doesn't matter right now. But you certainly can identify that behavior, so you see the critical point. If you, on the other hand, take h a little bit bigger than 1, even just a little bit, you see that the behavior of entanglement starts changing, because now you have correlation length in the system. And so you see that when the length of the system is still much smaller than the correlation length, you still see logarithmic behavior as expected. When the length of the subsystem is much bigger than the correlation length, what you see is saturation to a constant value. And the fact that the entanglement saturates in massive systems, this is also well known for a long time. I think Pasquale and John wrote it probably for the first time in their paper, and then was proven rigorously by Hastings. And this saturation essentially is proportional to the logarithm of the correlation length. So essentially you have a similar scaling, but now the L in the formula is replaced by correlation length, which is the natural real scale. So all of these things are understood. There is, in our work with John, the one I cited at the beginning, we went a little bit further. What we understood is what happens in the transition between these two behaviors. So essentially, if you have a system with a mass scale, we know that, okay, if the length of subsystem is very small compared to correlations, then you see log behavior. If it's much bigger, you see saturation. But there will be a region where the correlation length and the size of the system are comparable. And what happens in that transition region? Well, it turns out that you can describe that using methods of 1 plus 1 dimensional quantum field theory. And what you will find is that there are universal corrections to that saturation, which are exponentially decaying corrections, decaying on the ratio of this L here and the correlation length in the system. And this can be fully characterized using methods of quantum field theory. So this is something we did, and you can find in that paper. But let's talk about negativity, because I already passed half of the time almost. So how do we compute that? Well, one of the motivations people usually give to look at logarithmic negativity is that the entanglement entropy is a good measure of entanglement for pure states, but not so good for mixed states, because, well, in that case, it's not able to separate the entanglement that's purely quantum from the rest. It turns out logarithmic negativity is better to describe mixed states. It provides a good measure in mixed states and also for non-complementary regions, such as in the picture here. So if this is again my spin chain from before, now the question I'm asking is, I want to have a measure of the entanglement between A and B when I disregard C. And in this context, now it's a bit different. So A and B don't make up the whole system, they just make part of it. Now, if you try to find a good measure of that entanglement, people have come up with a measure, which is here, is this logarithmic negativity. And as you would expect, it also involves a reduced density matrix, but now it's a reduced density matrix of this system, A union B. So it's a bit like before, it's defined in the same way. I told you this is good to describe mixed states, but in fact the studies we have done, both in CFT and QFT, they usually look at a pure state, ground state, and even in that context, you can learn something new. So suppose this is your ground state of your system, you compute this reduced density matrix, and you put it into this formula. Now, if you look at the formula here, you don't quite have just the reduced density matrix, you have something else, a different matrix. This matrix here that has this superindex, this TB, this represents a partial transposition in subsystem B. So essentially, you are taking this reduced density matrix and you are transposing the degrees of freedom associated to the Hilbert space of subsystem D. That gives you a new matrix, and it turns out that this new matrix is not necessarily positive definite. So it can have negative eigenvalues, which is not the case with the original one. Because it can have negative eigenvalues and you want to take a log, that's a bit of a problem. So you can solve that by putting absolute value in there. Okay, so essentially, what we mean by this trace here, it means that we are summing the absolute values of the eigenvalues of this transposed reduced density matrix. Okay? So this is what we are doing. This is the definition. Now, it turns out that a replica picture can also be useful in this context, and this is something Pasquale, John, and Eric developed in recent years, and I'll tell you how that works. So essentially, instead of computing what I just told you directly, there's another way of doing it, which is by going through a replica trick, and it works like this. You can instead define something else, which is a generalization of this logarithmic negativity that now depends on parameter n. And what you do here is, instead of taking now absolute value, you're just taking this density matrix transposed, and you do a power n of it. And the tricky thing is that if you want to recover the logarithmic negativity from this, you then have to take a limit n going to 1. So again, we have the issue of analytic continuation from n integer to non-integer. But not just that, you have to take an analytic continuation from values of n that are only even values, which is a little bit strange as a definition, but you can, I think, easily understand why that is the case. At the beginning, in our definition, we had absolute values in here because we only want to have positive values. And so if we want to ensure that we are always adding positive numbers, we can only consider positive powers in here. That's the idea. But if we want to recover the negativity at the end, we have to go somehow from this set of values at positive even positive powers to the value at n equals 1. So that requires some analytic continuation of that type, from n even to n1. Okay. It turns out that if you try to do it from n odd to n1, you get something which doesn't have the right properties. And that's something that, again, Pasquale, John, and Tony investigated in some detail in the context of CFT. Okay, so why is it useful to use this replica trick? I mean, where do we go to from there? Well, the idea is that once you introduce these powers of reduced density matrices, both in the context of entanglement and in the context of negativity, then, well, we have come up with some ideas about how to specifically compute those objects in terms of correlation functions of some special field, which we call branch point twist field. And so the moment, in quantum field theory, the moment we can express something in terms of correlation functions, then we are in a situation where we can hope to compute something. So that's the advantage of this, and let me just try to describe it to you in a picture. So replica trick. So this idea of considering replicas to get to the phenomenon entanglement or to the negativity is an old idea. So it was already used at the very beginning by Callan and Wilczek, this replica trick, and it actually originates from the context of studying random theories, in fact. But the idea is that if you want to compute the trace of rho to the n, something like this, you're looking at matrix elements of this matrix rho, let's say, and remember that the matrix rho is a reduced density matrix, so you trace over the degrees of freedom of your subsystem A bar, let's say, like in my original picture for entanglement. So you have some degrees of freedom associated to subsystem A, where you haven't somehow closed this gap in here. So you have somehow a branch cut in that description. And then when you do power n, it's as if you took lots of these matrix elements and you multiply them together, but they are concatenated. So from the point of view of this picture, it's as if the upper part of the branch cut on one Riemann surface is connected to the lower part of the branch cut and the one above, and so on. Because this is a trace, this has to be cyclic. So the last one has to be connected to the first one. So by doing a sort of path integral description of this trace, you can interpret it as a particular partition function on a Riemann manifold which has n sheets which are cyclically connected. Okay. Now this doesn't seem like a huge progress because we replace the computation of von Neumann by the computation of something that looks pretty complicated still. But what is interesting from here is that it was realized initially by Pasquale and John and then extended by us later on. It was realized that this partition function can also be written in a different way. It can be written in that configuration I showed you. It can be written as a two-point function of two fields, which we then call branch pointwise fields. So this TTL is just a conjugate of T. And what these fields do essentially is, removing in a way the problem of dealing with this Riemann surface. So instead of doing calculations on this complicated Riemann surface, we are going to do calculations again on the plane, on R2. But the price we're going to pay is that instead of having our original model, we'll have n copies of it. And we're going to have an extra field, or pair of fields, which are associated to this cyclic permutation symmetry we have introduced by having all these replicas. And these fields are quite special. They have non-local commutation relations with respect to other fields in your original model, or in your n copies of your original model. So as I said, this is the idea that you could relate the entanglement entropy of an interval to a two-point function appeared first on the work of John and Pasquale, but then later on in our work, we really actually understood deeply the properties of these fields. In particular, we understood something quite important, which is how we could make sense of them as local fields in a replica model. And once these fields are local, we can do computations of their form factors, their correlation functions, etc.
Has ever been discussed whether there is no breaking of replica?
Breaking of replica.
What is the argument that?
What do you mean by breaking?
I mean, to take the random energy model.
Yeah.
Solved by, I guess, Derrida in the past, and you can do by replica, you can do directly, and the two things doesn't coincide.
I mean, I think so. I don't know if it's related to that, but I mean, the problem that often arises is that, I mean, if you do this replica picture, at the end of the day, you have to take a limit n going to 1. And I think.
Yeah, but since it's a limit, means that n is not integer. So.
Exactly. So, in my understanding, it's not that the replica trick in itself is a mathematical statement, which is correct, but what is non-trivial and which is not resolved is how you actually take that limit property. In other words, once you have computed this two-point function, how do you analytically continue that to n non-integer and then take the limit? Because that's what you need to do. And that's difficult. So, for example, in massive QFT, this n is going to be related to the number of particles in the theory. So, how do you actually do the step to go from that to making n non-integer? That is difficult. And it's not fully understood even in CFT. So, for example, if you have seen any talks by Pasquale recently, or you know about their work in negativity, they have been able to compute logarithmic negativity in the compactified free boson. But so they have a 4-point function in that case of twist fields, but they don't really know how to take n to 1 in that context because that 4-point function depends on matrices.
But before taking this limit, this is the point. Probably you can do, or probably you cannot do. It's technical.
Yeah.
But you should be aware that what you are doing is sensitive.
Yes,
right?
yes.
Because I mean, all the fame of Parisi is related that there was symmetry breaking.
Yeah.
So here it's there known. There is some understanding why this limit can be done.
So if I might say something, I think in the original paper of Pasquale and George and J. Stat, there are some comments about the fact that at least for the single interval you can do this.
There is no symmetry breaking.
Yeah, I think there is some comments.
I mean, I don't think there is a fundamental mathematical understanding of why that should work in every case. I'm not aware of it. I think there is quite some evidence that it works in QFT and in the cases we have studied, let's say. And if I have time, I'll explain a little bit how we deal with those problems. For example, the fact that this analytic continuation is not unique. I mean, that is a big problem. When you try to analytically continue these things to n non-integer, there are many analytic continuations you could take. So that arises, yes. So we have sort of resolved it by imposing some additional conditions on what these properties of these functions. So I'll try to come to that in a little while, if you let me. But just to say that It turns out that these twist fields actually had been studied by other people much earlier, unbeknown to us. Already clinicians, even before had had realized that these fields would be present if you consider, for example, CFTs in an orbifold, and they had computed their conformal dimensions. And if you know their conformal dimensions, it's very easy to see, for example, that from this definition here, you recover the logarithmic scaling I talked about at the beginning. So that would be the entanglement entropy of an interval. And also, you can easily see that if you have a massive theory and you're looking at a small correlation compared to the size of the system, then you expect this two-point function to factorize. And so you have indeed in the saturation to a constant, which is now going to be a function of the correlation length of the system. So you can recover the features you knew about from this description, which is already a good indication that it seems to work. Also from this description, you can see that because this is a two-point function, for example, for integrable models, you could now carry out a form factor theorem, compute this two-point function, and you would have corrections to this saturation behavior, which is essentially what we understood with John in our original work. So a little bit more about these twist fields. Essentially, in this replica theory, we are going to have other fields and copies of the original fields. If we have a very, very simple theory, like a free boson or a free fermion, which has just one field, we now have n copies of that field indexed by I, and the twist field has some very particular exchange relations with those fields that are non-local. In fact, what it does is to implement the structure of this Riemann sheet. So when a field goes around the twist field, it goes to the upper copy, or it goes to the low copy if it's the other twist field. It depends actually in which direction it rotates. Essentially, if it crosses the branch cut, there's going to be a change. If it doesn't, then it will remain the same field, like in this identity here. So by using these properties, you can develop a specific form factor program for these fields, in integral models at least, and then you can hope to compute their correlators. So this is what we did, but now let's turn to the logarithmic negativity. So in the case of the negativity, what you have is a description also in terms of twist fields, and this was described first by John Pasquale and Eric. And what you have in that case is that this function here, which depends on n, is actually going to be a 4-point function of these kinds of fields I just presented. And pictorially, it's actually easy to somehow understand that. In the case of negativity, we have this sort of picture here. We have two intervals, and it's a little bit as if in the boundaries between each interval we put one of these twist fields. So we have put a t here, a t tilde here, and then a t tilde here and a t. They are exchanged because of this transposition. So the transposition is what exchanges the t and the t tilde. So you're left with the challenge of computing this. Now, even if you're in CFT, computing 4-point functions is not necessarily simple. They have a universal part, which you can understand, but then there is a part that depends on the system. And in particular, if you're looking at twist fields, they are not known a priori. So this is difficult, and it's not fully resolved. They have actually studied this in a lot of detail for the compactified free boson, where these kind of 4-point functions are known, because these 4-point functions are partition functions in this complicated Riemann surface, and they have been studied by Dixon and others a long time ago. So even in that case, as I was telling, the continuation to n equals 1 from n even is not fully understood either. So this has been investigated. It's difficult, but there are particular limits that are easy to do. So of course, if you take particular limits here where this reduces to 3-point function or a 2-point function, then you can at least say something about that. And that's something that they did in their original work. And there is one particular feature which is quite interesting and quite beautiful about these twist fields, which is in particular the limit when these 2 points get very close to each other. So when the region C in the middle between A and B gets very small, we have something that they have called the negativity of adjacent regions. This is still a new quantity, different from the entanglement entropy. And when you take that limit, you need to make sense of what it means to bring these two fields close together. Now, if you understand the properties of these twist fields, you immediately understand that these two fields are two twist fields moving in the same direction, bringing you down through these copies. So when you put them together, what you get is actually a new twist field. They call it t squared. And this new twist field, what it does is to jump by 2 instead of by 1. So it also implements a cyclic permutation, but it doesn't visit all the copies. It just visits them in jumps of 2. And if you understand this, then you also see very quickly that actually it makes a huge difference whether you look at n even or n odd in terms of the properties of this field. Because, for example, if n is even, if you have an even number of sheets, then what will happen is that this t-square field is only going to visit half of them. If you're starting an odd number, you will only visit the odd ones. If you're starting an even number, you only visit the even. And that means that this field actually is the direct product of two twist fields for half the number of sheets. So essentially this t-square is t and half times t and half in a way. And that affects its conformal dimension and its properties also in massive theory. If n is odd, on the other hand, it's also easy to see that even if you go in jumps of 2, you will eventually visit every one of the sheets, every one of the copies. And so for n odd, this t-square field is actually another t field. It has the same dimension, it's just another permutation where the copies are visited in a different order. So n even and n odd made a huge difference when you do calculations. So it is no trivial matter to say that the analytic continuation really is from n even. Okay, so for example, by using these sort of arguments, what you find in CFT is that in that limit you have a 3-point function which you can then compute, and you find that the logarithmic negativity scales again with a constant which is related to the central charge. So again, you can get information about the central charge of your theory. Of course, because this is a 4-point function, if you tackle more general cases, you could in principle get information about the full field content of your CFT, but from a computation of negativity. But that's a bit more difficult. But it's all hidden in there. Yeah?
So what should I expect when R1, R4 are much larger than R2 or R3? So to separate regions, and this should be 0 in principle.
Yes.
Function, but it doesn't seem to be 0.
It doesn't seem to, is it, okay, so R4, you're
So
saying
then
R4 very large.
factorize, right? So
You should
R1,
factorize,
yeah,
yes.
but then it's not 0. Or am I wrong?
Is it not 0? Why is it not?
Why is it not 0? Or why is it 0? If this function gets factorized.
So when if you factorize this TR4, well, in the massive theory, so you will factorize, so you will get the expectation value of that field.
No, but there will be TR1, TR4 factorized with TR2, TR3 or not? Or I mean, would you expect to have two correlators, R1, R4 multiplied by R2, R3 or something else?
Yeah, I think it will
okay, but
factorize.
these correlators are not necessarily 0.
No, not necessarily.
That means the n will be non-zero when two intervals are largely separated, which is strange.
Right, okay, so you're saying these two very far from those two.
Yes.
It would not be 0. No, in that case, you get two 2-point functions, so you get
I mean, maybe I should normalize this n to something like that.
I don't know. Let me think about it. Okay, I'll tell you later. Okay. So, what can you do in massive theories? So in massive theories, well, we can take this definition and try to do a calculation in massive theory, and it's again difficult. 4-point functions are complicated, but there are certain limits you can do again, which are a little bit easier. One limit, we consider two in our work. One situation is when you take essentially the same limit that Pasquale and John and Eric considered. So we get this t-square field here. But in addition, you also take the other field, the one sitting at R4, this one here, as being very far from everything else. So this is a situation of adjacent regions with one of them being semi-infinite. And in that case, again, you get something which depends on a 2-point function, which you can hope to compute by the usual methods. You have a, well, expectation value in there, and you have this t-square field, which, as I discussed, has this conformal dimension at a critical point. So this will be the sort of configuration we are thinking about. So this region is very large, and the region in between A and B has now disappeared. And there's another configuration we considered as well, which is the case of disjoint semi-infinite regions. So when these two regions here are very large, but there is a finite separation between them. And in that case, in the massive theory, what you have is a decoupling again of the fields here and there, and you're left again with a 2-point function. But it's not the same 2-point function as for the entanglement entropy because you have two fields of the same type. So it actually has quite different features. So you can actually study these two kinds of 2-point functions. And what we did was to study this using general methods of massive QFT, 1 + 1 dimensions. And well, if you consider integral systems only, then you can do a form factor expansion of these 2-point functions. If you don't require integrability, you can at least say something about the first correction to these 2-point functions are dependent correction, because at least at the level of two-particle form factors, you can, well, you have all the features of the form factors are determined by kinematic requirements, which don't necessarily have to do with integrability. And so what I'm going to show you is really quite general, and I just show you the result. I won't have a lot of time to describe it, but at least I'll tell you what we get. So if we look at the adjacent regions case, well, when R is very small, we should recover the conformal behavior, and we do. So we have the behavior that Pasquale, John, and Eric found. So it goes like a C with log R, and then, well, in the way we wrote it, we will have some constant here. Of course, this constant depends on how you choose this cutoff, so it's not universal. But with our definition, this constant here has a particular meaning. It's related to 3-point coupling of these fields, whose value actually is unknown from CFT methods. If you look at the situation where a massive correction should matter, then you see first some sort of saturation as for the entanglement entropies, that you have a part that depends on the correlation length, on the mass, and you have a saturation constant here, which actually depends on the expectation value of this field for n equals a half, so actually you have to be able to compute that. And then you have other corrections, which are new. And these corrections, in particular, the leading one is this correction here, which is quite nice. So this is the most, this is the leading correction. As you can see, it's a Bessel function, and it goes with the square root of 3 times mass times r. So those of you that have done form factor expansions will not be surprised that the Bessel function comes up, because that's what you often get on a two-particle form factor contribution. But what is not so easy to see is why there's a square root of 3 in there. That is the non-trivial part, really, of this. You will never get that naturally from a form factor expansion, but you get it here because of the way this analytic continuation has to be performed. So there's something rather subtle about the fact there's a square root of 3 in there. And then there are other universal terms relating to the bound state. So actually, this quantity seems to capture something specific about the presence or not of bound states. And then there are other corrections which are going to be model specific. But this correction here, well, it depends on the mass spectrum of your theory, so it depends on the model in that sense, but it doesn't depend on the details of the S matrix, really. These numbers here, they're all the same for any QFT you look at. So that's quite an interesting result. If you look at the other limit, you also have a universal result, which is this one here, which now depends also on Bessel functions of different kinds on the mass spectrum of your theory. And again, well, you have a conformal limit and a massive limit.
So in the non-integral case, what I should think about just the bound states below the two-particle continuum of the lightest particle, including the bound states. Or
So this actually this summing here, which is of all particles, really this is only present here if there are bound states of a particle with its antiparticle, so alpha alpha bar bound states, and if the pole of this bound state is located in some particular region. So it's a bit, not all bound states will be captured, but some will contribute in there.
okay, but they're not allowed to sit on any continuum, right? Because otherwise your
No.
approach breaks down.
No, that's true. That's true. Yeah.
So like,
Yeah.
So if this is completely independent of the S matrix, means that I can take the free limit, right? Free limit.
Yes.
So
Good.
field theory and free limit is a bunch of harmonic oscillators,
Yeah.
completely separate one from the other. So how shall I interpret this result?
Limit. So you're saying that you shouldn't get an entanglement.
I don't know.
In that case.
I'm asking.
You have entanglement in the free case, right?
Yeah, but how shall I interpret it? I mean, I have completely separate options.
But they're not, they're spatially,
It's a spatial measure.
so free boson is entangled, right?
Yeah.
Momentum is true within space itself.
So in the sense that the theory behind are trivial, but the states again construct
Yeah.
theory down state.
Absolutely.
So if you had a free boson or a free fermion, you would just have one of these terms here, depending on the mass. And you have something similar for entanglement entropy of one integral as well. So you really do capture something.
Is it possible to compute this numerically using DMRG? Can they
It
tease
should be. It should
then
be.
you
So
could
that's
check
something
for it.
it would be nice people attempt to do. So if you were to compute this in a gapped system, and you subtracted the saturation value, then you should see a vessel function decay with, which is described by this function. So we are looking forward to somebody doing it, or us doing it with somebody. So that's a future project. In fact, this is being done for the entanglement entropy, where there is a similar correction. Yes.
Yeah. In fact, my question was about what's the difference, if there is any, with the entanglement entropy and this ability to.
For the entanglement entropy,
Yeah.
so for the entanglement entropy, you get also a correction similar to this. But you have a 2 here instead of a square root 3, and you have a 1/8.
Okay.
That's the difference. So that's yeah. So this we checked when I'm offering it numerically, and also Jesko Zerka has checked it for the theories. Okay, so these are the results. So of course there's some work in getting them. I didn't want to show you the calculations, a bit tedious, but I wanted to give you the key ideas of how this is done. In particular, what are the key steps on our approach to tackling this analytic continuation, which is a tricky question. Well, this is just some observations that this is a very general result, that actually the fact that it's so universal is based, or is due to the idea that what actually determines those contributions is the pole structure of the form factors, and that is, well, the same for any theory. It's determined by kinematic requirements. So that's why theories don't depend so much on the S metrics. Which means that from the negativity we get information about the spectrum, and we also get some information about some universal quantities, because as I told you, in these saturation constants, we have expectation values of these twist fields, and we have a 3-point coupling in CFT, and these are all quantities which you could in principle access from QFT methods. So if you do numerical simulations, you should be able to see this, which is what you were saying, and this has been done for the entanglement entropy by us and by Jesko Zerka as well. So let me tell you something about the derivation. It follows, well, first of all, if you look at short distances, of course, it's all CFT, and this has been done by these people I already mentioned. If you want to see corrections, of course, what you have to do is study these 2-point functions that arise, and you can do that using these twist fields and using their form factors. And what is most tricky is that you have to find a prescription for finding the correct analytic continuation from n even to n1, and this is always the sticking point, the slightly tricky point. So I'm going to just show you, give you some details for this particular case, the TT square case. So if you look at short distances, or the conformal limit, if you want, you would expect, well, some scaling behavior, which is understood. And also, when these fields get together, essentially a T and a T tilde kill each other, and what comes out is another T tilde. Essentially, this is due to the cyclic permutation properties of these fields. So the leading term in the OPE is not the identity, it's another twist field. And so you get some things like that, okay? And so also, when you take the limit n going to 1 of all of this, you end up with this kind of result I showed you earlier. This is just, so this C1 is the limit n going to 1 of this 3-point coupling. And this T actually doesn't really give you anything, because when n goes to 1, actually the expectation value is just 1. And this is due to the simple fact that when n goes to 1, you don't have replicas. So the twist field when n goes to 1 should be the identity field. So it has 0 form factors, and it has expectation value which should just be 1. So this becomes very, very simple, and so that's where this result comes from. If you want to look at massive corrections, of course, well, the first of them is the saturation is obtained when R is very large. In that case, these two fields decouple. And then you have to remember that this T square I told you earlier for n even is nothing but 2 T's, but acting on half the number of sheets. So when you take n to 1 and you use that, what you end up with is an expectation value for n a half. And again, this requires, well, I mean, computing those expectation values, they're actually not known for most theories, just for free fermion, and we are trying to do it for free boson now. But they're quite tricky to get, but if you have an analytic function of n, eventually you can do this computation at a half. So you have this saturation constant there. Now the rest, the Bessel function contribution comes from looking at the next correction to this. Okay, and that's done with form factors. Now I'm not going to show you the details of that, but I'm going to show you the reasoning of this, the ideas. Okay, so essentially when you do a form factor calculation or expansion, remember that this n essentially is the replica number, and that means that you're taking the spectrum of your original theory, however many particles it had, and you multiply that by n, so you have n copies of that. And that means that when you will do form factor expansions of correlation functions, typically you will have, well, lots of integrals and rapidities, as you would normally expect. And then you're going to have functions of the form factors, which will depend on lots of indices which run between 1 and n, because you have to count every particle, essentially. And so once you look at this, you already stumble across the first problem with analytic continuation, which is that n appears here in this sum. So it appears in a non-analytic way. Now, we came up with a way of resolving this, which seems to work very well. We already did that in our work with John a few years ago, which is that actually you can do a very simple trick. People usually call this a cotangent trick. So essentially, you can replace sums by integrals, by contour integrals. Essentially, you can, instead of having one of these sums, let's say, you can have a contour integral of the same function with a cotangent function which has poles exactly, whose residues exactly reproduce this sum here. That's the idea, okay? Now the price you pay, you would say, is that you replace, then you have contour integral of a function of n, so you have something analytic in n, but the price is that you have to compute that contour integral. It turns out that that contour integral has some features that are, some of them are simple, and in particular when you take the limit n to 1, which you often have to do in this context, this becomes simpler than you would expect. So you can actually get rid of any integrals in a way. You end up with some function of theta and n, or lots of thetas and n. Okay, so you have to believe me on that, but it just works rather well. Now that step itself, you could criticize because of course this analytic continuation is not unique, in the sense that when you do this sums in n, of course you could add a function which is 0 for every n integer, but it's not when n is non-integer. So there are many choices you could make, and you have to find a way to filter out the ones you don't like. So the criterion we used in our original work, and we have used since, is something that comes from Carlson's theorem. And Carlson's theorem essentially gives you a condition under which you can be sure this analytic continuation is unique. Now you can ask whether this condition is something we should desire, but it seems to work for every model we have looked at. It seems to work very well. It singles out a particular function, and you can then take that function and do consistency checks, and we have never found any problem with it. So that's the extent of our evidence. So Carlson's theorem tells you that if you have a function which diverges with n, as n goes to infinity, in some limited way, so with some q smaller than pi, then you can argue that its analytic continuation is going to be unique with that condition. And the form factors involved in this expansion seem to satisfy that property. So, now you have then an integral of an analytic function of n. Okay, now you can say, okay, let's put n equals 1, or whatever limit we have to take. Well, that's actually still tricky in a sense. So, as I told you earlier, the form factors of this twist field at n1 actually should all vanish, because at n1 the twist field is the identity. So what you often find is that after doing all of this, it looks like you get 0, or you get something close to 0. But that's not quite right. So there's something a little bit more subtle to consider. But they don't get 0, but they simplify a lot, precisely because n equals 1 is a very special point. Okay? The only thing that we realize we have to be careful about is about what happens to the poles of these functions you're integrating as n approaches 1. And so if you think of this analytic continuation as a process where you start with an n integer very large, and then you approach 1, okay, what you have to do is to consider if there are any poles in here, in the rapidities, which cross the real line as n approaches 1. Or in other words, they are in the upper half plane for n large, and then when n goes to 1, they pass to the lower half plane, or vice versa. Because these integrals are all between minus and plus infinity, you have to count the residues of these poles if they exist, and add them to your result. Okay? Actually, it is by doing that that we get this Bessel function square root 3. Okay? It turns out that if you do this carefully, for the two-particle contribution, in that case, you find there's a pole, I think, at I/3 in the rapidity when n goes to 1, and that is what ends up giving you this square root 3 in there, coming from the cos theta half in the argument of the Bessel function. So these are the basic 3 steps, okay? So this is not a mathematical proof. It's a plausible argument, and it's one we have tested in various ways, so we feel rather confident about it, but it's not the end of the story. Still, I'm quite happy with it in the sense that I think we are able to do a bit more than the CFT still, because at least we are able to take this limit in some way, which in CFT seems to still be a challenge. Just one little comment I want to make before I finish. So this is responsible for that term in there. This is where the square root 3 comes from. Now, if you want to consider completely general QFT, essentially one particle form factor and two particle form factor corrections, I think they are the only ones that you can tackle in complete generality. If you want to look at further corrections, then the only thing I will be able to do is to look at an integrable model where we can fix those form factors. For the twist field, in fact, the form factors are known completely just for free fermions and free bosons, just because you can use Week's theorems and you can know everything. So one thing we have been doing recently is to look at the free boson. Now the free boson theory is so simple and so nice, and this analytic continuation works so well that we have been able to do something quite remarkable, I think, which is to actually reproduce this behavior here. So if you look at this two-point function, which was involved in one of the limits I was discussing, to compute the logarithmic negativity, you would consider n even and take n to 1 in this two-point function. If you look at short distances, so r small, you should recover the CFT behavior. And as you know, it's hard to see that from form factors because it means you have to add lots of them to see that behavior properly. It turns out in the case of the free boson, by using these ideas about analytic continuation, you can actually find this power d precisely. You can sum this whole form factor series or find an explicit formula for it. And you can show that you get the number that CFT predicts. And actually what we do from a form factor calculation, which I will show you, it will be published soon, what we get is that this d here can be expressed in this complicated way in terms of some hypergeometric function. And I haven't been able to do this sum to prove that this is this number, but CFT tells you that this power here should be 1/4, and if you do the numerics, you get that number very, very precisely, okay? And not just for n equals 1, but you can get that for the n's, even and odd, and you always find agreement with the CFT prediction. So I think this is a rather powerful test of these ideas about the analytic continuation, because these ideas are involved along the way to get to this formula, so they seem to work, okay? So that's just to show you that a little result.
Can I ask? I mean,
Yeah.
so it's supposed to be a quarter, you say, but it's not a quarter.
You mean it's far? It's too far?
No, I'm puzzling what the statement is.
No, the statement is that CFT tells you exactly what this power should be.
It's a quarter.
It's a
that's
quarter.
what you
It's
said.
0.25.
Yeah.
And if you do the numerics, I mean, here is summing, I don't know, I think I sum up to 200 terms or something.
I see. So
Okay, so it's
basically,
not-
if you
no,
do
no.
the whole sum, it will be a quarter.
If you do
That's
the whole
statement.
sum, I'm quite convinced it was, yeah. So I should say this is numerics, okay? So I don't know how to do this. I mean, I've looked in Untitled and haven't found the way to get through it yet. But I mean, I'm pretty sure that should be a simple result. So if any of you knows the trick, just tell me. But numerically, it seems quite clear that it works very well. Okay. So, yeah. I did something with Mathematica, yeah.
One time we did this.
Yeah. Okay. I didn't know about that. But it's pretty close, nevertheless.
Check your version.
Yeah. Okay.
Is it possible to extend this to D, say, or 3D or something? You are working with 3 particles.
3D, with higher dimensions or higher numbers?
Higher dimension.
Higher dimensions. It should be possible. That's something we would like to do actually. But I mean, this whole idea of the twist field, in principle, it does have a generalization to higher dimensions. It's just that instead of being a field sitting at a point, it's going to be what people sometimes call surface operators or line operators, because these fields are associated to the boundaries between regions. So if you're in higher dimensions, that boundary won't be a point, it would be a line or a surface. And so, yeah, in one dimension more, it would be a line operator. So a bit like a Wilson loop or something like that. So I don't think anybody has tried to do it that way, but that's something we would like to think of in the future. It would be interesting because then you could see what happens in higher dimensions from this approach. Okay, so I just conclude, almost on time. So I hope I convinced you that essentially you can use QFT methods to compute measures of entanglement and get some new results. and that these results exhibit at some level remarkable universality. So very often the idea of universality within entanglement measures is very much related to critical points and CFT. But actually, if you have theories that are massive, there are also features that are very universal. So these measures of entanglement, they also tell us something about QFT, massive QFT. Well, they tell us something about the mass spectrum, they tell us something about the presence or not of certain bound states. So this is all something that would be nice to test in the context of gapped spinching. So there's some numerics that have to be done. Of course, there are many extensions of this we are working on already. One is, for example, this free boson, which is we can tackle in full generality, and we're writing a nice paper about that. But of course, we would like to go beyond two-way functions. And so, okay, that's a bit more complicated, but we have already started. And I think in the context of integrable models, at least, there are more things that we can say about those 3 and 4-point functions. And it would be nice to have physical interpretation for this. So I go on a bit about this square root of 3 because I was very happy when I found it. But I mean, I told you earlier that for the entanglement entropy of one interval, there's also Bessel function correction, but that correction in that case goes with Bessel of 2MR. So you have a rational number in there. When we wrote that paper with John, later on Benjamin on his own wrote a paper where he actually showed the results extended to non-interval systems as well. Our paper was for interval systems. And in that paper, he actually gave an interpretation of this 2MR in there as related to the production of pairs of particles. But how do you interpret that root 3? I don't know. So I don't know, maybe there is some nice physical argument as to why that should appear. In any case, first of all, it would be nice to test whether this really agrees with some numerics. So thank you very much.
When you compare with numerics, you usually use lattice systems and probably some DMRG code,
Yeah,
right?
yeah.
So you have another length scale, which is lattice spacing, right?
Yes,
So you have
yes.
to
Yeah. So this lattice spacing is
so
essentially.
the correlation length should be much larger than lattice spacing when you do numerics.
Yeah.
But
I
you will
mean,
get additional corrections as Xi array or something like that.
yeah. So this lattice spacing actually essentially is this epsilon equal my formula. Yeah. This ultraviolet cutoff.
Is it possible in numerics to distinguish actually these corrections due to lattice spacing from corrections?
I
I don't know.
Is it possible? Yes, I think
Yeah.
so. Because when you do the numerics, essentially, any result you get in the chain, let me see if I have the general formula somewhere. So when you do the numerics, essentially, this quantity here is the length of your subsystem, and is already expressed in terms of your lattice spacing. So the lattice spacing is.
Your correlation length should be also larger than the lattice spacing, I guess.
Yes, very
So
much
there will be
more.
corrections as Xi array.
Yeah, I guess so. Yeah, but I mean, this. Okay, at least in the numerics we have done, they didn't seem to affect the results very much. We did reproduce this Bessel function behavior very precisely. So but I guess yeah, that would be something to consider as well. But what I wanted to say is that the fact that the lattice spacing matters is hidden in the non-universality of this cutoff in here. So there's always this epsilon in there, and so that's why this saturation here is some non-universal constant, which doesn't have particular importance. But what is interesting is that, like for the entanglement entropy, when you take the saturation near the critical point minus the saturation away from the critical point, you get rid of that epsilon, and then that difference really is a universal constant. It's something that just depends on this number here and on that number there.
And these numbers you can calculate from your theory. Or you have
In some
to
cases, yeah. I mean, in principle, yes. So this is an expectation value. Expectation values are very tricky to get, as Sergei will know. He's computed some. But I mean, there are some quantum field theories where you can access it. For example, for free fermion, you can know that. For free boson. This 3-point gapping here, I don't think anyone has managed to compute this analytically yet. But in principle, you should be able to get that from CFT.
So you have free fitting parameters.
Yes. So I mean, when you do your numerics, you will get some constant here, some constant there, and then if you compute their difference, this is going to have to do with the difference between this and this. So that's what you will be able to say. Yeah. But it would be nice to be able to compute this analytically. That would be nice.
If you try to do the free case using supersymmetry, you could presumably avoid the replica trick altogether.
We haven't tried, no. So, free case with supersymmetry.
Well, I just mean, so usually in disordered systems, if you want to represent the logarithm, right, you take a n-1 over n and you take the replica limit to represent the logarithm.
Okay,
But if it's free,
yeah,
usually you don't need to do that. You just introduce a copy of the system with opposite statistics.
Right,
and you don't
right,
need to take the limit. So, I mean, your whole setup, I guess, is designed for the replica trick because you've got these multiple reading sheets and twist fields, but
Yeah.
presumably for the free case.
in the
you might
free
be able
case.
to avoid
I mean, so, for free theories, there are results that can be gotten without having to use this twist field approach, especially for the entanglement of one interval. In fact, the way the entanglement was computed originally had nothing to do with twist fields. It was just based on using conformal symmetry and conformal maps, and on the fact that when you just have a single branch cut, you can map this Riemann surface back to the complex plane, and you can use this mapping to compute everything. But when you have more complicated geometries, these twist fields seem to be useful because even in CFT there is no map that brings you to a simple geometry. So either you know those correlation functions from some other source, for example, because they are partition functions, there's some funny geometry that somebody else computed, and that's, I think, as far as I know, is only available for compactify free boson, or otherwise using the twist field is the only method that I know to access that. So yeah, it depends what you.
It probably involves twist fields, but maybe you don't need n copies of them. Maybe you have to introduce twist fields for the other sector or something.
Yeah, I mean, there will be, of course, if you have a symmetry in your theory, whatever it is, there will be a twist field associated to it. So twist fields, I mean, we didn't invent them, they're just symmetry fields. So there are theories, like in the easy model, you have one because there's a C2 symmetry, so you have your sigma field, for example, and that's a twist field associated to that symmetry. So you may have fields associated to other symmetries, whether they do the job of reproducing a measure of entanglement, I don't know. I mean, in free theories, for example, in the free fermion, you can actually relate this twist field to twist fields of AC. Well, yeah. So you can, for example, relate their expectation values in some way. But that's just because free theories are very special. So I don't know. Yeah.
I was going to ask, so in the free case, again, you can deduce the reduced density matrix just by demanding that it reproduces the correlation functions of the inside the interval.
Mm-hmm.
Can you do a similar thing for this partial transpose matrix and get it the calculation that way?
For the free case, I mean, depends. So I think for the free fermion, this is, yeah, it can be done. So I mean, my point of view is, I think very much about 4-point functions. So in the case, I think of the free.
You get the reduced density matrix, it's Gaussian, as you say, but you still have to calculate the integral entropy from it, and that's where the difficulty lies.
What's going to put
Even in the free case.
Yeah.
I'll
Yeah.
do that.
Well, actually, the free fermion is particularly complicated because the fundamental field is non-local with respect to the spin. So this creates a lot of difficulty in evaluating these density matrices. Yeah.
Masha, imagine you start from the free theory,
Yeah.
and then you switch on interaction, say, Sinch-Gordon, just the simplest one.
Quench.
Now, no, you just adiabatically move
Okay.
the coupling.
Okay.
So what I want to understand is the mass when you switch on the coupling, Sinch-Gordon, get renormalized.
Yeah.
So there is a dependence on the coupling. Not as not.
It should
And
be.
everyone really check what entered this formula.
The mass, you mean, the mass
Yes.
scale enters the formula. If anyone checked.
No, because there is a dependence on coupling constant, the actual mass, certain scheme, right?
Yes. So it's been checked to the extent that, so for the entanglement entropy, not for the relativity, but for the entanglement entropy where you have a similar correction, and there are things to write. Just write it briefly. So, oops. So for the entanglement of one interval, find this or you have saturation and then one direction. 1.8, some modern masses, okay.
Okay.
So has this been checked? Well, so numerically, yes. For some
Varying G. Varying G, varying the coupling constant.
No, varying the coupling, no. It's been checked for, not varying the coupling, for specific theories. But varying the coupling, I don't know, yeah, we should see, I guess we should see a change on that mass scale, so a change in the correlation length. So when you do a numerical simulation, I mean, in the end, this is essentially the correlation length.
You know what is the bizarre thing? That in each Gordon at a central point, the mass gap is 0. So if you vary G, I don't know how this function is behaving.
I don't know. I mean, it hasn't been done. But, yeah. I guess it would, yeah, I think it would be interesting. I think, so, I mean, numerically what it's done is that the correlation length is identified by computing some correlator on the theory. So you have correlation length, and then you look at entanglement, and you see if you can find a fitting to a function like that with that correlation length identified. And well, for some theories like XXZ and XY and so on, this works very well. But nobody has looked, I think, at varying that mass scale and seeing what happens. It's an interesting idea. I don't know, but the prediction is that the formula is the same for any theory.